Okay, so yes, we had or have Newton's first law, okay, which deals with inertia, and for the most part, running around a track can be more difficult for some people more than others because as you're going, well, not so much people because we're not going fast enough, but for anyone who follows NASCAR, why is that a challenge for some of them cars going around that curve, going 120 miles per hour, maybe? Why is that? What does that inertia want to do to that car? Remember, it's going around a curve, so it's curving to the left. So what's that inertia doing to that vehicle? Not wanting it to let it go left, but push it what? Into the right, into the wall. Okay? So when you look at racetracks, how are they designed then? Yeah, they got an embankment where it goes around the curve so that compensates for that inertia. Okay? So that's the first law. The second one can be stated really easily by what? Force equals, I thought maybe you're nodding your head because you knew. No? Oh, okay. But yes, force equals mass times acceleration. That's exactly correct. Okay? If acceleration is not given and it's talking about a weight, we have a weight that's also measured in, you could say our weight is in newtons because, well, you might be thinking to yourself, well, how's that possible? Well, this is, let me pull up the presentation so I can blank out the screen. Okay. So what we mean by that is this is where we left off with. Here's your force equals ma. So we said, don't mess with ma, because ma is a what? Ma is a force. So don't make ma mad. Does that ever happen? I think we do that all from time to time. Okay. This doesn't mean anything to you, but what we're talking about, okay, so a force we know is measured in what? Newtons, okay? And that equals a mass that's measured in what? Kilograms, okay? Times an acceleration measured in what? Okay? So, if we are referring to gravity, it has a value of 9 what? 9.8, okay? And that's meters per second squared. So that has an effect on us. Does our mass change whether we're going from here to the moon to Mars? Does your mass ever change? No, it does not. Okay, but if you were the type that, let's say 30 years down the road, you wanted to say, I need to lose some weight, why can't we measure ourselves on the moon? What about the gravity on the moon? You would be much lighter. Your mass is still the same, but here on Earth, our acceleration on our mass is 9.8. On the moon, it's 1.67. Okay? So what that means is forces is also a way of measuring weight. You could just take your mass times 9.8, and that could be your weight in newtons. Okay? Because when you step on a scale, okay, it's that downward pull on gravity that when you're stepping on the scale, of course, there's some springs and some different types of mechanisms in there, whether it's a balance or one that is a digital type. It spits out a reading in pounds, and that gives you a weight as well. But our weight can be also measured in newtons. So on the paper that's going to be given to you, that's not due until when? Not due until Friday. But does that mean, oh, geez, I have till Friday to get that done? What would probably be the best thing that you can do? Work on it when you can. because I don't know about you, but I'm busy too. This isn't the only class that we have in here during a daily basis, and this isn't the only class that you're taking on a daily basis. Okay, so I like to think that that is a given, that should the time be given to you, take full advantage of it. Okay, so enough of that. But one of the things I wanted to, we're going to get this started, and I don't know how far we're going to get, but when we think of the activity that we're going to do, this will give you somewhat of an idea of what it is we're actually measuring. That activity is not this week, and next week I'm really not sure, but it deals with forces. Okay, so as we look at that, it'll give you a better idea on what's actually happening with these forces. And we had said in class, when you hear or think of the arch, the architectural design of the arch, that's associated with who, do you think? What civilization? The Romans. That's right. Not to say that the Egyptians weren't good builders, because they were. Why could we say that? Let's pull out the pyramids. They're still standing, of course. And if we look at modern engineering, is it possible for us to build that? I honestly don't have that answer. We might think we have the technology, but do we have the ability to build that precision? I think the answer is no. Okay? And sometimes if you look at Victorian era woodworking skills, okay, to replicate that is very difficult. Okay, so those skills maybe have come and gone, and with that, again, I honestly don't think we can build the pyramids today. I really don't. So, is it myself, Mr. Hammer, or
I just was coming in to look and see how our freshman class is doing.
okay?
So, not even here.
Okay, all right. Anyway, so getting back to this, right, this will give you a general idea of how what we do is. Does anyone think they know what a precast is as far as pouring concrete or cement? And I wouldn't expect you to know, but bridges are usually put together in pieces. Okay? One of the things when you go through Sioux Falls, if you're going south on the interstate, you can see this company called Gage Brothers. I'm not sure if you know anything about that, but that's a company that makes a lot of moldings for putting bridges together. So what you're going to do is design a mold and put, I wouldn't say popsicle sticks, but pieces of wood in there that you're going to have to be responsible for bending them, designing the bend or precast for that, Can we shut this overhead off? Not yet. Okay. Okay, now does everyone have it? Okay. All right, so notice that as we look at that problem, it had said this race car driver crashes into a wall, and it's asking two questions. What's the first one? What's the force? The second one is what's the pressure? And remember, we said a lot of these concepts build upon one another. Okay? On your formula sheet, you're going to want to write this down. Okay? And that is that pressure. Now we got to be careful with that because you might get that variable mixed up with what? Momentum. So you can do one of two things. You can just put a line over the top. You can put a smiley face over the top. I don't care. Or you can say Y, whatever it is you want to use for that variable for pressure. Just so you know that that's the formula that it stands for. Okay? So I'm still going to stick with this P for pressure because all pressures equal a force that's measured in newtons divided by not an acceleration, but what was the last number given in that problem? It was 3.84 what? Meters squared. Any length that is squared is a what? It's an area. Okay? So this is not force divided by acceleration. It's force divided by what? So there again, I wouldn't put a line over top of that. I would just do maybe like a zigzag like this. Or maybe use the letter B. I don't, depends what you feel most comfortable with. So now we've got our new formula. Pressure equals a force in newtons divided by an area. Okay? So this is measured in meters squared. This was measured in newtons. So when we label pressure, we can say newtons per meter squared, or we can do P, I want to say PC for pascals. Okay? So that is your label for pressure, is pascals. Okay, so you've read the problem. The next thing you should do is what? So what do we know in this problem? And what else? Okay, so what's the mass? Okay, what else do we know? What else do we know? Okay, so however it was that you did that, that's, Need to be able to keep them two variables separate, okay? So the area equals what? Okay? So what is the question ultimately asking? We want to know what the pressure is, okay? But notice, to calculate a pressure, we need to know a force in an area. Well, we've got the area, it's right here. But what are we missing? But do we have enough information to calculate the force? Yes, we do. How do we know that? We take these two together, because that's Newton's second law, is any force equals a mass times acceleration. So, force equals, now that we have this wrote down in a nice concise area, 1673.14 times 6.44, because that's what the formula tells you to do. Okay? And upon doing that, 1673 times 6.44 times 6.44, we get 10,077 or 775, excuse me, 0.02 what? Newtons. Now, notice we have our force in newtons, we have our area in meters squared, so now we can solve for this guy. The formula says we need to take our force, divide it by the area, so pressure equals what we just calculated, 10,775.02 divided by our area that our formula tells us to do, 6.44, sorry. So what does the pressure equal? Oh, I was looking at the wrong one. You're right. I thought I was right the first time. I was just seeing if anybody was paying attention. Can't get anything past you people. Okay, so what's our pressure then? These two divided by one another. We'll just say 2,806. Again, that is pascals then. Okay. We went through that really. Yes. Could you repeat that? And I bet it's PA is actually, I just used PC, but now that I think about it, I do believe it is PA for pascals. Okay, we went through that really quick, but forces are nothing new. The area might be something new in this class, but it's something that you've been doing in math class a lot. But now we can calculate pressure. So left outside, do we understand? Are we on the bus? Okay, left middle, middle, right middle, and right outside. Okay, so for those of us who were saying, well, we kind of get it, you have a multitude of opportunities to obtain that information that you feel you are lacking in understanding. Okay, so got some time that you can work on these should you choose. We will pick up with this again tomorrow.